Hello, class. So today we're going to talk about 6.3 solutions about singular points. So last time we saw how to solve differential equations that look like this. So you could have a function of x, another function of x times your derivatives, and another one here. And we solved them about ordinary points, which is basically in situations where you don't have division by zero. So we solved those with power series. But this time we're going to consider situations where we have power series about singular points. Okay, but it depends on how the singular point looks, whether we can do this technique or not. Okay, so about singular points, i.e. where, so what we said last time was you divide by the a2 function to make it look like this. And then wherever this is not analytic, for the two middle functions, which basically happens when it divides by zero, and there's division by zero. So when these are not analytic. Okay, but we can only do this sometimes. And so here's when we can do it. So we can only do this for regular singular points. And they'll be pretty easy to identify. But here's what they actually are. So a singular point is regular, or a regular singular point, if when I look at these things, so I'm going to look at these two things, okay? So if, and I'll just rename these, I'll use some new names here. So I'm going to call this little p of x. So if I take, sorry, I should name the singular point x naught. So if I take a factor of x minus x naught and I multiply it to this middle thing, and I do the same thing, so I'll call this q of x, little q of x, but this one is squared to the other function in front of the y. If I do this, and they're both analytic, at this point, that's what it means to be regular. So again, you're really just going to be looking for division by zero. So if it's not this, then it's called irregular. Okay, so for most cases, you're looking for division by zero. There are other ways to not be analytic, like with logs and stuff, but mostly it's going to come from division by zero. Okay, so let's see an example here. Okay, so x squared minus 4 is my a2. 3x minus 2 is my a1. And 5 is my a0. Okay, so if I want to think about it with all these labels up here, so you don't have to like write all this stuff, but I'll do it for this one. So a2 is x squared minus 4. Oh, sorry, I also want that to be squared. Forgot the square there. And then a1 is 3x minus 2, and a0 is 5. Okay, so what am I looking for? Well, when I rewrite this, I guess this is called standard form. The dE becomes this. So I just want the y double prime to not have any extra coefficients. So I divide it out. Okay, so now this is how it looks in the other form where I have a2 over underneath everything else. So now where are the singular points? Well, if I just factor out the denominators, oops. Actually, well, I should factor out everything, but everything else is already factored out. But if I factor out x squared minus 4 is x minus 2, x plus 2. Now they're both squared. Then what I'm looking at is, where are these not analytic? It's when you divide by 0. Okay, so the singular points are x equals 2 and negative 2, because these things are not, first of all, not analytic at these numbers, because they cause division by 0, just as the quick way to think about it. So you're not going to have a power series representation there, but it's easier just to think about division by 0. So first of all, they're singular for that reason. So which ones are regular? So, and which one is irregular? So now I look at, I guess I'll call this one, I call it P of X. So I look at this function, the one that was in front of y prime, and I multiply it by, so let's do x not equals 2 first. Okay, so if I multiply by x minus x naught, so x minus 2, that's where that's coming in. If I do this and I work it all out, I just get nice cancellation here. I get this. Okay, the question is this analytic at x equals 2? Yeah, when I plug in 2, I don't divide by 0 anymore. It's analytic everywhere except for negative 2. And if I do q of x, where I multiply by x minus 2 squared, and I use the other function, the one in front of the y, I also get cancellation here. So I get 5 over x plus 2 squared. So these are both analytic at this number. So this is a regular point. Okay, so it seems like a lot to check or something, but it's really not, because if you just sort of go back up to this form here, when I'm going to multiply by x minus 2, what I'm looking for is factors of x minus 2 on the bottom, and if there are too many, because what's going on here is I'm multiplying by 1, I need all of them to be gone for this to be analytic, and because this one is already here, I have enough to cancel them all away. And then for q of x, I multiply by 2 of them to cancel these 2, and so there are enough to cancel them all away. If there was more powers of x minus 2 on the bottom, then this wouldn't work. It would be not analytic, and that's going to happen for x equals -2. Okay, so for x equals -2, when I do the same thing, so I'm going to multiply by x plus 2. X minus -2 is x plus 2 to my function in front of the y prime. Now I'm only going to have, when I'm finished canceling everything out, I'm still going to have an x plus 2 on the bottom, so it's not analytic there. So it's irregular. Didn't pass the little test. So I don't even have to check the second part of the test because it's got to pass both. Okay, so it's irregular. So the little shortcut is, for problems like this at least, is you really just want x minus x naught at most one time under y prime. If there's more, then they're not going to cancel enough. And then at most 2 times under y, under just y, for the same reason, because you have the x minus x naught squared. That's not going to cancel with more of them if there's more of them. So now we could do examples more quickly. So x equals 0 is regular for xy double prime minus 2xy prime plus 8y equals 0, because when I write it in this other form, what's my x naught this time? X naught is 0, so I have 0 factors here, which is less than 1, and I have 1 factor here, which is less than 2. And I need it to follow these 2 things here. But if I have more powers, so x equals 0 is irregular for something like this, because when I write it in the other form, by dividing the x cubed, now I get too many powers of x. This is more than 1. And this is more than 2. So I have too many powers of the division by 0, basically. So that's the shortcut to figuring out if it's regular or irregular. You can also have complex numbers be singular points too. So for example, this one has 2 regular singular points. Plus or minus 3i for this thing, because when you divide it out, those are the 2 zeros of x squared plus 9, basically. So you get this. And they're singular because they cause division by 0 again, but they're regular because when you divide it out, for both of them, you don't have too many powers. So you only have 1 power for each, which is what you need for this to work. So here, there's only 1 power of each factor, which is what you want. You want 1 or less. And here you want 2 or less, 2 or fewer, and there's still only 1. And as long as there's 2 or less, it's fine. Okay, so that's what you're looking for as the shortcut for determining if they're regular or irregular. Okay, so now how do we actually solve these things? Okay, so we can only solve it about regular ones. So that's why we want to classify it, but we're not going to even try irregular ones anyway. So sort of a little bit of a waste of time to think about it too much. Okay, so to solve a differential equation about a regular singular point, we use something called the method of Frobenius. It's going to be a little bit unsatisfying. Sort of just, as usual, plug something in and it just works without too much figuring out why, but that's okay. Okay, so the idea is this. So if, whoops, what happened to my pen? Okay, it's working all of a sudden. So if x naught is a regular singular point, then there will exist at least one, so there could be two, but there's going to be at least one solution of this form. So it's going to look like a power series, but multiplied by this extra factor of power of r. And once again, we're just going to always be centered at 0, so it's going to be less complicated than this usually. And then, of course, you could bring that power in because it's the same type of thing and add the powers and write it like this. So where is this valid for? So because x naught is a regular singular point, you can't actually have a power series at x naught. So this is on not the radius of convergence doesn't work exactly at x naught. So we write it like this. So it's between 0 and r, meaning if you just draw it in a picture, it looks nicer. So right at x naught is not valid. So maybe I'll draw a big X there. But you can go out the radius of convergence in either direction, and it's valid everywhere in between. So this would be x naught minus r, x naught plus r. So it's not valid right at x naught, but in this little region here, that's where this series is a solution. Okay. Okay, so in this method, we have to determine r and an. Okay, so just like before we would determine the an's using some sort of recurrence relation, now we do that after we figure out r. Okay, we determine r and then the coefficients of the power series. But it's going to work very similarly. We're just going to plug it in and see what happens, just like last time, sort of. So it's best to see it with an example. So first, x equals 0 is a regular singular point. And if you want to see why again, when you divide it out the 3x, it causes a little bit of division by 0, but not too much. Only one power on the denominator of each, which is fine, as long as you don't get 2 in the y prime term and 3 in the y term, then you're fine. Okay. So that means we can guarantee that this fact is here, that we can guarantee a solution. We just have to do all the work now. Okay, so now we've just plug in y equals this is the first one. So for y prime, last time we would start the series at 1, But here, actually, it's going to start at 0 again. And then the derivative is going to work the same after that. So we bring the n plus r down and then subtract 1 from the power. So why are we starting at 0 this time? Well, if you expand this out and take the derivative, you'll see that the first term doesn't necessarily disappear anymore. So we still have to keep counting from 0. So if you like write this out, then the derivative would be, the first one would be a0 r x to the r minus 1 and so on like that. So the 0 term is not gone, so we still have to count from 0. So that's why we couldn't skip to the n equals 1 term like we did before. Same thing will happen here. We can't skip to the n equals 2 term, but everything else will work the same. Bring down the power and subtract 1 from the power. Okay, so we're going to plug these in. It's easier to plug it into the original form. So the first form that it starts in is a lot nicer to work with, but this other form is how we check if it's a regular singular point. Okay, so we're going to plug this in. You need a lot of room here. So 3x times the second derivative. Now this is going to take a very long time to simplify down until it looks nice, but that's okay. Okay, so then plus y prime. The algebra gets a little bit messy, so you do want to be careful. And you can try to skip ahead and if you want, but I don't know, it's easy to make a mistake. Okay, so what we're going to do here is bring in the 3x in the first term, and I'm going to do it in a very specific way just to make things easier. You can do it differently, but I'm going to do it like this. So I'm going to bring the 3 in and multiply it into the second factor here. Okay, so it looks like that. Then the x goes into the power to make this be one higher up. So now it has the same power as the second one. So that's good. And if you look at the book, they do it differently, but you could follow it like that if you like. All right, so now we have this. Okay, so now I'm going to put these two together because they have the same power of x. And so I'm going to factor out, I'm also going to factor out x to the r from all 3. So let me do that first, actually, to make things a little bit easier. So x to the r comes out of each one. Then here I have an, n plus r, 3n plus 3r minus 3, x to the n minus 1. So the other one also is x to the n minus 1 because I also took out the x to the r. So I'm just going to go ahead and combine the two series now, like this. And now they're both with the coefficient or coefficients of x to the n plus, n minus 1, because I took out the x to the r. All right. And then minus this other one I haven't touched. And there it goes. Okay, sorry, my pen sometimes stops working. Okay, x to the n plus, oh wait, I took out the r, the x to the r, so that's all that's left. Okay. Great, so now I have this giant thing. So now the problem is one is at x to the n minus 1, the other is x to the n. So what I have to do is take out the first term or sorry, no, I'll do that in a second. I have to add 1 to the power and subtract 1 from the starting place. So now the first one is going to start at -1 because I'm going to subtract 1 there and add 1 to all of the ends you see here. That'll become 3n plus 3 when I switch that to n plus 1. So just taking a quick little shortcut there. This will become plus an plus 1, n plus 1 plus r. Now x to the n. So now I have the same starting coefficient. The same power of x, which is good, but not the same starting coefficient. So to fix that, I'm going to take out the -1 term. So I'm going to actually plug in -1 for n. That way I can start at 0. So I'm going to plug in -1. So I get a -1 plus 1 is 0. -1 plus 1 is r. And then I have, let's see, if I plug in -1 here, I get, let's see, the 3's canceled already. So I would get 3r minus 3. Is that right? Because n equals -1. Yeah. And then, so that's that coefficient plus a0 times, and then over here, I just get r. And then all of that is times x to the 0. So I plugged in the 0th term because now I can combine these into a single series because now they both start at 0. And then I could factor out the x to the n from everything. So I have a n plus 1, n plus 1 plus r, 3n plus 3r plus a n plus 1, n plus 1 plus r. So now I've factored out x to the n from both of them, minus an, and all of that is times x to the n. Okay. So just simplifying a little bit to clean it up. So that becomes, let's see, a0. I guess I could factor out the a0, and then it becomes, what is that? 3r squared minus 3r plus r. X to the 0 is 1. And then over here, I think I also want to factor out n plus 1 plus r from the first two terms. So I can think of it as an plus 1 times. So if I factor out an plus 1 from the first two, so I'm factoring this out, and then I'm factoring out n plus 1 plus r, then what's left is 3n plus 3r plus 1. And let me just check that work for now. Just to make sure I'm on track, because if I make a tiny mistake, then this can screw everything up forever. Okay, looks like I'm good. Okay, minus, okay, so that's all attached to the an plus 1. All right, minus an x to the n. Okay, on track here. Okay, so then just like before, now we're going to set the coefficients are all equal to 0 because each power of x on the right is 0. So that's the only way that this could be true. So what we can say now is a0 times, this would be 3r squared minus 2r. That has to be 0. And this coefficient up here, an plus 1, which I'll just sort of get ahead and add the an over. We always end up doing, divide the n plus 1 plus r over 3n times 3r, sorry, times this thing, divide that as well. Okay, so that's coming from here. setting that equal to 0, and then solving. Okay, so then here is where we solve for r. So we don't want our a0 to just be 0, because then everything would just be 0. So what we want is the other part to be 0, this thing. So if I factor out an r, I get this. So I get r equals 2/3 and 0. That's my two values of r. Okay, so what this is saying is there's two values of r, which make this be a solution. This thing long, long ago, this thing is a solution for these two values of r. Okay, and for each value of r, you get a different series, is what's going to happen here. So we're going to get two series solutions, although we are guaranteed at least one. And the two series will come from the two choices of r, but they both use this same recurrence relation. Okay, so this gives us two power series solutions, one for each r plugged in to this thing that we got here. Okay, so if I plug in r equals 2/3, I'll get one relationship to help me find the ANs, and then if I plug in r equals 0, I'll get another relationship. Okay, so let's do 2/3 first. Okay, I'm gonna call this R1 because there's two of them, so R1 and R2. So if R1 is 2/3, then AN plus 1 will be AN over n plus 1 plus 2/3 and 3n plus 3 times 2/3 plus 1. So we can make this look a lot nicer so we don't have to deal with fractions. If I write this as n plus 5/3, and this would be become 3n plus 3. What I could do is factor a 3 out from the second one, and multiply it into the first one so that I get something that looks a little bit nicer. 3n plus 5 n plus 1. Okay, so that's the relationship for r equals 2/3. So then plugging in values of n. So we started counting from 0, I think. So n equals 0. Yes, that's right. 1, 2, and so on. Now, if I plug them in, so I get A1 is going to be A0 over, so I plug in 0, I get 5 times 2. I'm sorry, 5 times 1. Then if I plug in 1 to get A2, it'll be A1 over, what is that? 3 plus 5 is 8 times 2. But then I plug that in for A1, then I get A0 over 8 times 5 times 2 times 1. And we'll start to see the pattern emerge here. So what we'll notice, which is different than last time, is every single term is going to be based on A0, not on A0 and A1, like back and forth or something. They're just going to always be based on A0. So that's one interesting thing that will happen. Okay, let's do one more. So when I plug in 2 here, I get, what is that, 11 times 3. And we can start to see the pattern now. When I plug this in one more time, I'm going to get this sort of thing where I start at 5 and I always add 3 to get to the next one. That's like that grouped up there. And then I'm going to start getting this factorial here as well. So in general, the AN term is going to look like A0 over. So you're going to start counting at 5, then 8, then 11. And it's just going to go until, how is it related? How is 11 related to 3? in this way and 8 related to 2, it's going to be just based on this thing up here, sort of, 3n plus 2. And then the factorial that you're on is based on the term. So a3, 3 factorial, so n factorial here. Okay, so that's the relation for r equals 2/3. Okay, so that tells us that y equals, I'll call this y1 because there's going to be 2 of them. So it originally looks like this. Now we know r is 2/3 creates a solution. So I'll plug that in specifically. Just to make it look nice, we're always going to factor that out to the front. Okay, where an now is this relationship that we just found. So if I sort of write it out a little bit, we'll see the typical pattern that we're always going to write it as. So when you plug in 0, you just get a0, and then you start following the pattern after that, because then you get a1x, a2x squared, and so on. So what we're going to do is rewrite these all in terms of a0, like always, and then factor out the a0. And the other terms, so like a1, for example, looked like a0 over 5 times 1. Those other terms, they follow this pattern that we found here. So we're just going to plug that in for the rest of them. So the 1 is always going to sort of be sticking out here because it's coming from factoring out the a0. Whoops, and then here we're going to start counting out 1. Okay, so start counting out 1, and then just plug in the pattern, except we factored out the a0, so it's going to look like this. X to the n. Okay, so that is the series solution. That's one of the series solution. That's for r equals 0. Okay, or sorry, r equals 2/3. So just keep that in mind for later. What we're going to do is eventually we're just going to get rid of this a0 completely when we write the general solution. So the idea being a0 can be anything, so you're just going to think of it as a parameter and call it like c1 or something. Okay, so then instead just call, so I think I called this y1 before. We're just going to get rid of the a naught because it's just a parameter. We're going to call y1 the same thing without the parameter. So let me just write it one more time here. So long. So these take so freaking long. Okay, so this is the solution again without the parameter now. Power series solution. Okay, so we're just going to call it that. Then when we write the general solution, we'll put a C1 as the parameter in front of this thing. Okay. Okay, so in any case, let's get y2. So now use r equals 0 to get y2. Okay, so we're going to do the same exact thing with 0. So r2 equals 0 gives us an plus 1. If you go back to your original thing and you change r to 0 now, you get this. Okay. Then you plug in everything like before. So you get a1 is a0 over 1 times 1. a2 is a1 over, so now I got 2 times 4, which you plug in a0, you get 1 times. I'm going to write it in a weird way. I'm going to put one of the ones with the 2, so 2 times 1, and then one of the ones with the 4, 4 times 1, just to see the pattern emerge. Okay, A3 is A2 over, so now I'm plugging in 2, so I get 3 times, that's 7, and so I get A0 over, so I'm going to write it as 3 times 2 times 1, and 7 times 4 times 1, to sort of see the same pattern as last time. So in general, it's starting to look like this. So you have some n factorial again, 3 factorial, 3. So it's going to be another n factorial, and then the 7 times 4 times 1 thing is going to look like just that same pattern, adding 3 over and over. So it's going to be, it's going to end up looking like 3n minus 2. Okay, to get to the last one. And then you have the n factorial. Okay, so then plugging these in for y2 now, once again, we're starting again with this thing, x to the n plus r. Now we're plugging in r equals 0. So it's really just that. And then when we plug this thing in, we're going to just sort of follow the same logic. So the x to the 0 would come out, although you don't have to write it this time. The a not term would come out, and then we just get rid of it again. And then inside here is the pattern that we figured out with the a not factored out and gotten rid of. So it's just a quicker shortcut, which we want to take advantage of because it's going to take forever if you write out every single step every single time. Okay, so that's y2. Then the general solution is we have 2 linearly independent power series solutions. So the general solution will just be their general linear combination. So we're just going to write it like this every time so that we don't have to write out the power series again. But it's where this is y2 that we just found and y1 was up above. Okay, I'm going to pause and take a break, although it won't seem like a pause to you, but maybe you should take a pause as well. All right, I'm back after a break. Okay, so that's one example of solving something like this. And just to name some more things, the equation that we wrote down earlier, r times 3r minus 2 equals 0, that we had to solve to get r, that has a name. It's called the Differential equation. So it sort of determines how everything's going to work. And there is like a little formula to figure it out earlier, but we're just going to sort of figure it out the same way every time. Feel free to use the book if you want to see how that works. But it doesn't hurt to just write it out every time anyway, since it sort of happens on its own. Okay, so let's do another example just for more practice. Solve 2x y double prime plus 1 plus x y prime plus y 0. So again, here you can see right away that this is a regular point at 0 because you divide by 0, but not too much, not too many powers of it on the bottom. So x equals 0 is a regular singular point. So we're guaranteed at least one series solution, maybe 2, using this method. So, okay, and it's going to work the same. So again, we're always going to do x equals 0, just take too much time to do even more types of examples. So it's always going to be centered at 0. Okay, so let's plug this in again. It's going to be the same series to start every time because it's just x to the r added on to what we had before. And then just to save a little bit of time, that x I'm going to distribute in ahead of time. And that 2, as well. So that's going to work the same every time, for me at least here. So it's going to be an n plus r, and then I'm always going to put the 2 into the next term. So it's 2n plus 2r minus 2. And then the power of x goes in to take the -2 to the -1 instead. Okay, so I'm skipping a little bit of the first steps from before. Okay, and then 1 plus x times the next series. And so that one looks like an n plus r, x to the n plus r minus 1, and then no coefficients over here. Okay. So now when we distribute this giant thing into this little thing, so one of them will be the same, and one will have a power of x added onto it. So the one that's the same is going to be able to combine with the first series because they'll both be x to the n plus r minus 1. Oh, sorry, this should be n plus r way over here. And then the other one will combine with the last series. And I'm going to take out the x to the r again. Okay, so x to the r is going to come out of everything. And then here, like I said, it's going to combine with the next series. And so they're both going to have an x to the, I took out the r and minus 1. Okay, and then the other two series are both going to be x to the n, because the x multiplies in to give you x to the n plus r. I took out the x to the r. The other one was already x to the n plus r. So they're the same power. So I'm going to combine these two now. And they're both x to the n. Oops. So they're both x to the n, so I can go ahead and write them like that. Okay. So again, I have to subtract 1 from the index to add 1 so that they're all x to the n. So I'm going to do that again. So this will become x n equals -1 to start. And then I'm going to have to add 1 to all the n's here. So it's very, very similar. That'll become 2n plus 2 when I substitute n for n plus 1, plus 2r minus 2. Here, this is a n plus 1, n plus 1 plus r. Okay, so now those are all x to the, now this will be x to the n. So just like before, I'm going to have to take out the -1 term to start at 0 so I could combine it with this other one. All right. Okay, so let's take out the -1 term again, just like before. So if I plug in -1, I get a0. Then I get r. Then I get, so those 2's minus 2's cancel. Then I plug the -1, I get 2r minus 2. Then over here, I plug in -1, and I just get a0 again times r. Okay, and all of that is times x0, which is 1, so I'm not going to even bother writing the x0 this time. So now both series will start at 0. So now I can combine them all into one big series. So this will be a n plus 1, n plus 1 plus r. The 2 and the 2 cancel. This is just 2n plus 2r. And then plus another an plus 1 term here. So those are later. We're going to factor that out again, just like we did in the next step. Okay, so that's from the first series. Now I can put it with the second series because they both start at 0 now, and now that's all x to the n equals 0. Okay, so one more simplifying stage is typically all you need. So this looks like a0 times, so you can simplify it however you want, but I'll do it the same way as last time. So this is 2r squared minus 2r plus r. And then over here, just like before, I'm going to write my an plus 1 term out. So I'm going to factor this out from both, basically, of those two first terms. So it's going to be an plus 1 times n plus 1 plus r. And then I factored out that from the first term, so all that's left is 2n plus 2r. And from the second term, all that's left is a 1. Okay, so that's all for an plus 1. And now I factor out an here, and I do the same type of thing. An plus r plus 1 is left, because I took out the an from the and to get that 1. And now all of that is times x to the n. Keep forgetting my end bracket over here. Okay, so just like before, this gives us the indicial equation. So I get 2r squared minus r equals 0, or r times 2r minus 1 equals 0. So I get 0 and 1/2 again. I get two different r's again, which I think is going to give us two series solutions again. We'll see. Okay, and then from the other part, setting this whole coefficient equal to 0 gives us, when you solve for an plus 1 again, so you subtract the an term over and divide the stuff that's being multiplied to an plus 1, just like before. Luckily, these will cancel. That'll simplify things a little bit. And now we get this. Oops. An plus 1 equals negative an over 2n plus 2r plus 1. Okay, so that's our relationship. And now we just have to plug in the two values of r and get the two series solutions. Okay, so r equals 1/2. That will give us an plus 1 equals a negative an over 2n plus 2, or like you could write it like this. And then r equals 0 will give us an plus 1 equals negative an over 2n plus 1. All right, so now we just start writing out a couple terms to find the pattern. So let's see, a1 will be for over here, so I'll cut it like this. So this will be negative a0. So now I'm plugging in n equals 0 and so on. So plugging in 0 gives us the first one. I get 2 times 1. Then a2, you get negative a1 over 2 times 2. And then plugging that in there, I get the double negatives. So I get negative a0 over 2 times 2. I'm going to group together, and then 2 times 1. So here we're going to get a pattern that's a little bit easier to write than the last one was. So this would be much more of like a test question where you can actually see the pattern and write it in a nice way. So let's write one more. So negative a2. So now it's another 2 times now a 3. And so you get negative a0 over 2 times 2 times 2, 3 times 2 times 1. Here we can it's much nicer to see the pattern. So what's going on is, how many negatives do you have? You have -1 to whatever number you're on. So when you're on A3, there were 3 negatives. Then you have just a bunch of 2's. So how many? Well, you have 3 of them when you're on A3. And then n factorial. You have whatever factorial you're on is the same as what the index is. Okay, so 3 factorial, A3. Okay, so that's that one. R equals 0. The pattern will be pretty similar, I think. Not as nice. So A1 will be negative A0 over 1. And each time you're just going to multiply by 2n plus 1, which is an odd number. So you're just going to get odd numbers multiplied together. So, whoops, that should be A2. So then you get negative, 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 A0, 5 times 3 times 1, and so on like that. So still you get the negative changing back and forth and the amount of negatives is always whatever the index is on, but on the bottom, it's just multiplication of odd numbers, the last one being 2n minus 1, I guess. So when you're on the third, that would be 6 minus 1 is 5. Okay, so those are your two ANs. So now just to sort of use the shortcuts, so y1 is x to the 1/2. So that corresponds to r equals 1/2 times 1 plus, so this will always be the same. You take out the A0, then you rewrite it as 1 plus the series, starting at 1. Then you put your AN here. Okay, so that's very, whoops, that should be 2 to the n. There's a little typo there. Okay. Not in class, nobody could tell me about my typos. I know 2 to the n and factorial. Okay, so that's your y1. Your y2 is x to the 0 because of r equals 0. 1 plus, and now it's this thing. Okay, so that's the sort of faster way to write this, to finish this type of problem, is it always works like this. Okay, and then y equals c1 y1 plus c2 y2 is the general solution. Okay, so it'll take forever. So the last part of this lecture is just going to be a little summary of things that could happen. So I'm not going to do this whole next example, but I want to just say what will happen if you work it out. So if you look at this one, solve x y double prime plus y equals 0, you will get r equals 1 and r equals 0. And what's weird, they will give you the same solution. They will give the same series. So remember, you're only guaranteed 1. And in this case, that's exactly what happens. You only get 1 solution. Y equals, it'll turn out to be this. Pen is dying from being used so much. It's terrible. It looks like this. This is what you'll end up getting. Come on. And factorial, and plus 1, x to the n. You'll be able to take out 1x. So you'll get the same series twice. Okay, so this can also happen. So then what's y2? Well, okay, that's where these 3 cases come in. If you get the same series twice, then you just have to do this other little thing. Okay, so let's break this into the 3 cases. So case 1. This is sort of what this is what the examples showed us. So R1 is bigger than R2. They're distinct values. So I'm just picking the bigger one to go first. And what happens is when you look at their difference, it's not a positive integer. So it's like a fraction of some kind. So we already did one like this where R1 was 2/3, R2 was 0, R1 minus R2 was 2/3, which is not an integer. It's a fraction. Okay, so if it's not a positive integer, then you'll get two solutions. Then there will be two linearly independent power series solutions. So that's like the examples we did. So you get your two power series solutions, and then your general solution just looks like the linear combination of them. Let me write it like this instead, sorry. So it'll just be like something like this. So there'll be distinct power series, so you'll have different coefficients. ANs and BNs will be different patterns, and the two Rs will be different. Okay, so you'll get your two solutions, and your general solution will just be what we've been doing. So case 2, if you get, so I'll just call R1 the bigger one again. If this time it is a positive integer, so that was the example we didn't do, like R1 being 1, R2 being 0, then R1 minus R2 is 1, is a positive integer. If you get this, so 1, 2, 3, 4, 5, any positive integer, not 0, but a positive integer, then two linearly independent solutions this time are, so the first R will definitely get you 1. So that'll be the same as what we did. But Y2, if you have what we did in the have as a result what we did in the previous example, or we didn't actually do, I guess, but here, then your second solution might have this factor of ln of x, which is sort of how it comes from what we did before. It was like that section that we skipped, and then we used it once for the Cauchy-Euler equations. So you could have that Y2 looks like the first series, or sorry, A series plus the little extra. But it could just be two series again, because C might end up being 0. So C is some number, could be 0. Okay, so that could happen as well. It's sort of the most annoying case because like it could happen. But case 3 is nice again, because for sure something will happen, which is a little bit easier to deal with. And that's if you get R1 equals R2, then you get two linearly independent solutions, being one of them is just the power series that you'll get by doing what we did. And then the second one will be this fixed by multiplying by ln of x. So Y1 will have to be multiplied by ln of x, and then you'll have this extra series that starts at 1. Okay, so I don't know if we're going to do any of the cases like this. This is already long enough, so we'll see how the homework goes, but hopefully it's just like always like case 1, which is the nicest situation. Okay, so that's it for this video, finally. Ooh, all right, see you later.